Math 1314, Section IC1, Spring 2022, Tyler Junior College, Section 5.5, Point Slope Form, Parallel and Perpendicular Lines. Video 3, Perpendicular Lines. So far, we've learned the following in this section. Number one, if a line contains the point x1, y1, and has slope m, then the point slope form, PSF, of the equation of the line is y minus y1 equals m times open parentheses x minus x1. Second, two lines are parallel under one of two conditions. A, the lines have the same slope, or B, both lines have an undefined slope, meaning that the lines are both vertical. But we're also going to talk about, excuse me, about perpendicular lines. And I think most people know what perpendicular lines are, but let's answer the question, what makes two lines perpendicular? And there are two ways to answer this, geometrically and algebraically. I think most people are familiar with the geometric reason that two lines are perpendicular. They intersect at a right angle. Oops, didn't mean to see all that, so don't look at that. They intersect at a right angle. In other words, they look a little something like this. Well, we'll just draw it here. Okay. We would have one line that looks like this. Let's get this in a color that we'll see. And we'll have another line that looks something about like that. And they intersect right here at a right angle, which means it makes a 90-degree angle, a perfect square corner, if you will. But we're looking at lines algebraically as equations. And so it makes sense to ask the question, what makes two lines perpendicular algebraically? Well, their slopes are, let's figure that out by looking at a picture I have drawn in Desmos. Here we have two perpendicular lines, and I can rotate them. And you'll notice I got a couple of triangles drawn on each one. We can interpret these triangles as triangles used to represent slope. For example, if we were to take a look at this line here with the blue triangle underneath it, then we could say that the slope of this is the rise over the run. In other words, why don't we do this? Because I want to be able to draw on this. So give me 1 second. I'm going to do a screenshot, post it here, and you can't see what I'm doing right now, but in a second you will. It's not what I wanted to crop. We'll crop it right here. All right, let's blow this up. And now you're about to see what I'm looking at. Okay. So I just took a screenshot of this because I wanted to be able to label some of these things as rise over run. I think we need to take this font size down a little bit. So if this were the run of the first line, and this line over here were the rise, then for this first line, we could say that the slope, give me a second to get ready to draw here. Where'd the word run go? Well, that didn't work as well as I wanted. Let's try that again. All right, so rise, I mean. All right, so there's the rise of that line. All right, now we can draw this. So we can say that the slope of this line, we'll call it M1, is rise over run. Well, yeah, of course, that's what slope is. Why can I not draw this S? There we go. Golly, this is looking horrible. I don't know why this is not drawing very well. There's supposed to be an E there. Okay, can we just pretend that says rise? And then overrun on the bottom. Having a very hard time writing letters here. There we go. All right, so we can say that that first line is the rise over run. But look at the second line, the one kind of going a little steeper with the purple triangle to the side of it. It may not be obvious from this picture, but that purple triangle is the exact same size as the blue triangle, which means that the lengths and the sides are the same, except they trade places. For example, the rise on this one, and again, I'm not sure why it's not letting me draw very well, is equal to this run. Because we rotated that triangle. And what about the run on the top triangle? Is it equal to the rise on the other one? It is. So when you rotate this line 90 degrees and you follow that, golly, I don't know why this is not letting me draw. This rise right here. So when you rotate this triangle to get to the perpendicular line, the rise and the run trade places. So you might think that means that to get the slope of when two lines are perpendicular, their slopes are reciprocals because the rise and the run are trading places. And that's almost correct, except for one other subtle but very important difference. If we were to keep track of the rise and the run in terms of the direction they went, then look on this bottom triangle as we move from left to right. That's a positive direction. And when we rotate it to the purple triangle, we go from bottom to top, which is also a positive direction. But what about the rise on the blue triangle? It's currently moving from bottom to top, which is a positive direction, positive in the Y direction. But when we rotate that blue triangle, that side now points this way, meaning that the run is from right to left, which is a negative run. So it's actually the opposite of what that is. Now, what does all this mean? Because this picture really was a lot not as good as I wanted it to be. Well, algebraically, here's what happens when you find two lines that are perpendicular. Number one, the rise and the run trade places, meaning that the slope gets reciprocated. And number two, one of them switches from a positive direction to a negative direction. In this case, the run here, that actually stayed in a positive direction. Left to right is positive, bottom to top is positive, but the rise, let me find a color that's not being used yet. Here we go. What used to be the rise became the run and switched from going in a positive direction to a negative direction. So not only do the rise and the run reciprocate, one of them changes signs. So what does that mean in terms of lines and their slopes? Well, if the rise and the run trade places, then the slope gets reciprocated. But if one of them changes signs, then that means the slope also changes sign and becomes the opposite. So what it means is this. If two lines are perpendicular, then their slopes are opposite, meaning that one is positive and one is negative. Reciprocal, meaning that they get turned upside down. Slopes. Now, that didn't go as smoothly as I wanted. I wanted to be one of those aha moments. I think I failed. So let's just summarize what it means for two lines to be perpendicular. Two lines are perpendicular algebraically under one of two conditions. Condition number one, their slopes are opposite reciprocals. Now, this is equivalent to saying that their product is -1. For example, if one of the slopes is, we'll say 4/5, then the second slope, first off, would be the reciprocal, because when you rotate that picture, the rise and the run trade places. And it would be the opposite because one of the rise or run goes from moving in a positive direction to moving in a negative direction. So that's an example of opposite, one positive, one negative, reciprocal. Fraction gets turned upside down. Now, if you multiplied these, 4/5 times -5/4, you would get -20/20, which of course is -1. So it's equivalent to saying that their product is equal to -1. Now, there is one exception. The exception is when one doesn't have a slope at all. And if that's the case, that means it's a vertical line, perpendicular to vertical is horizontal, and a horizontal line has a slope of 0. So if their slopes are not opposite reciprocals, that means that one has a 0 slope and one has an undefined slope, meaning one line is horizontal and the other is vertical. All right, so we're going to do a couple of things. We're going to determine which of the following lines are perpendicular, and in the next one, we will find the equation of a given line. All right, determine which of the following lines are perpendicular. In this class, if you see the word perpendicular, you should immediately think opposite reciprocal slopes. If I can get this to draw. Again, if you see the word perpendicular, you should immediately think opposite reciprocal slopes, meaning that, I'm going to get my picture out of the way because my picture's in the way, meaning that they're reciprocals, one turns upside down to get the other, and one is positive, one is negative. So since we're going to be comparing slopes, we should probably find slopes. And if we're trying to find the slope from an equation, then we probably want to put the equation in slope-intercept form. Now, luckily, the first equation is in slope-intercept form, so we can see its slope right here. Let's just call that M1. The first slope is 3. What's the slope of the second equation? X equals 1/3 y plus 7. If you said 1/3, I fooled you, because this line is not in slope-intercept form. To be in slope-intercept form, it has to say y equals. So we're going to solve for the y by isolating it. First by subtracting 7 from both sides to get x minus 7 equals 1/3 y. And then to finish isolating the y, we can multiply both sides by 3. That would cancel the 1/3 and leave a y equals. Granted, it's on the right. And on the left side, we could distribute to get 3x minus 21. And at this point, we could observe that the slope of this line is also 3. So our second slope is 3. These aren't perpendicular because 3 and 3 aren't opposite reciprocals, or equivalently 3 times 3 is not -1. We could, however, say that those two lines are parallel. All right, well, let's find the slope of the third line. Well, to find the slope of the third line, we need to put it in slope-intercept form. We can do that pretty quickly by subtracting 2x from both sides. Cancel. Gives us 6y equals -2x plus 22. And then divide everything by 6. All the terms on the left, all the terms on the right. We get y equals, we have -2/6, which reduces to -1/3 times x, plus 22/6 will reduce by 2 to give us 11/3. But we're only looking for the slope, and it's worth mentioning that the y-intercepts have no play in this. Our third line's slope is M3 equals -1/3. And if you'll notice, this slope that we just found is the opposite and reciprocal of 3. If you think of 3 as 3/1, then the reciprocal is 1/3, and 1 is positive and 1 is negative. So these two lines are perpendicular, but those aren't the only ones, because the first line also had a slope of 3, which means that the first line is also perpendicular to the third line. So we had 2 pairs of perpendicular lines. All right, for the last example, you know, the timing of this couldn't have been worse. I had this all ready to go, and not that it matters, but I have a doctor appointment in 19 minutes, and I kind of have to get there. So I'm going to end this video now and do a follow-up video that does this particular question. Thought I could get it done in time.